start where we left off in the last session, which was the problem of finding the diameter of a tree. So remember we said that given a tree, and this is an unweighted tree, the diameter is the maximum distance between all pairs of vertices. So I look at all pairs of vertices, I look at the distance between them, and I take the maximum, and I call that the diameter of T. And sometimes I also just say diameter vertices. I mean vertices that have this maximum distance from each other. Now, in the last session, we saw how we can calculate the diameter using dynamic programming. In this session, we're going to find it in a different way. So just to refresh your memory, the idea here was that for every vertex U, I defined of the subtree rooted at U. So what is the maximum distance between two vertices if I can take these two vertices only from U and its descendants? And then we basically said that I look at U, I look at the children of U, and I say either these two vertices that have the maximum distance are in the subtree of the same child, or they're in subtrees of two different children. If they're in the subtree of the same child V, then that's just D of V, and of course I take the maximum over all the children. And if they're in the subtree of two different children, V1 and V2, then of course, in each of these, I want to go down as much as possible. So it would be 2 plus height of V1 plus height of V2. And we've seen how to calculate heights. Now, here's an interesting idea. Look at your tree. And of course, we talked about these levels and depths and heights and so on. But let's look at depths. Let's look at the distance from every vertex to the root. And let's call that level. So I claim that if we trace this dynamic programming and see which vertices it's actually choosing, it always chooses at least one of the leaves that are at the very last level. So for example, here, if I say this is level 0, this is level 1, level 2, and level 3, I have this leaf 7 at the last level. And I say that my dynamic programming always chooses 7 as one of the endpoints of this longest path in the tree. Okay. Now, you can prove this by just tracing the dynamic program, but I want to do this without dynamic programming. So I want to say, if I take any arbitrary vertex as the root, and if I want to find the diameter of the tree, I can always be sure that one of the endpoints of the diameter is one of the vertices that is farthest from the root. Okay. Now, let me give you a pictorial proof. This is the kind of proof that you cannot write in your exam, but it just gives you the intuition for why this works. So I have a tree, let's say it's rooted here, and then I have the longest path in this tree, okay? So let me show this longest path in red. So let's say the longest path is between these two vertices. Now, maybe this longest path goes through the root, maybe it doesn't, right? I don't know. So anyway, this path goes up to some place, and then it goes down and gets to this other vertex. And this place, this is actually the lowest common ancestor of these two vertices. We're going to talk about that later. But anyway, there is just one path between these two vertices. These are my diameter vertices. And it's going to have a highest node at some point. Maybe that highest node is the root, maybe it's not. Okay. Now I'm saying, take one of the vertices that is as far away from the root as possible. Let's show it like this. Let's say this is the vertex that is as far away from the root as possible, right? Now I can look at the path from this vertex to the root. I do something like this. Let's say this is the path. Now, if I have something like this, then you can already see that I can change one of these red vertices to the purple vertex, and I can get a longer path, right? In this case, I was taking this path before, but now I can take this path, and it would be longer, right? Now, if the purple path somehow went through here, then I could take this path, and it would be longer. Right. Now, you can formalize this on your own. In any case, this is our greedy algorithm and our pictorial proof that I can always pick the vertex that has the longest distance from the root, and I can say this is one endpoint of my diameter. Now, if I have several of these vertices, I can take whichever of them I want, because again, I can do the same thing that I did here. It's just that my path remains the same size. It doesn't get any longer. Okay. So based on this, I can have a different algorithm for finding alternative algorithm for diameter. Well, first of all, I want to find the vertex that has the largest distance to the root. So I can do this by a BFS, because the BFS always gives me distances, but I'm talking about a tree. So because I'm using a tree, it doesn't matter if I do a DFS or a BFS, because remember, both of those algorithms just gave me a subtree like of the original graph that touched every vertex. They all gave me a spanning tree. And if my original graph is already a tree, they're just going to give me the original graph. So whenever we're talking about trees, it doesn't really matter if you're doing DFS or BFS. You can actually do DFS and just calculate distances using DFS, right? So this is my algorithm. I'm going to say first, choose an arbitrary vertex as root. So choose some arbitrary root. Let's call it R. I always choose 1. You can choose whatever you want. And then just do a DFS from R, or do a BFS from R, whichever you like, to find the distances. So do a DFS or BFS from R. And then use this to pick one vertex that is as far away from R as possible. Okay, so let U be a vertex with maximum distance to R. Okay, now again, I say a vertex because maybe there are several. You can choose whichever you want. Now I know that U is one endpoint of my diameter. How do you suggest I find the other endpoint? Well, I can just do a DFS or BFS from U, right? And just find the farthest vertex from U. That would be the other endpoint of my diameter. Now do a BFS or DFS from U, whichever you like. And then let V be a vertex with maximum distance to U. Now my diameter is the distance from U to V, and my two vertices on the two ends of diameter are U and V. So based on what you want to output, you can just say output U, V, and the distance from U to V, whichever you like. Okay. Now, what is my runtime here? I'm basically doing DFS or BFS twice. And DFS took ON plus M, but this is a tree. So it has N minus 1 edges. So N plus M, it's basically N, so it's ON. So the runtime that I'm getting here is not very different from dynamic programming, but it's kind of interesting that we could just do this with DFS or BFS, or we could do it with dynamic programming. Okay. Now, I want to extend this a little bit, and we will see that we can extend both of these approaches. And here's the extension. Let's say that in the input, I just give you some tree. So I give you some tree T with vertex set V and edge set E. Okay. And as usual, this is not directed. I haven't chosen a root. All of this is up to your algorithm. So the input just gives you this, and there are no weights on any of the edges. And in the output, I want you to tell me for every vertex, what is the farthest vertex? Okay, so the output is this. For every vertex U, write, I don't know what to call this. Let's call it alpha of U, which is the maximum over all vertices V of the distance from U to V. I could also ask for the farthest vertex. It doesn't really matter. It's like pretty much the same problem. I can ask, what is the distance from U to the farthest vertex? Or I can ask you, what is the farthest vertex from U? Both of them will be solved using very similar algorithms. Okay. Now, how would you solve this one? Well, a simple solution would be that I start from every vertex U and do a DFS or BFS and see what is the farthest vertex, right? That would take n squared time because I have n starting points, and for each of them, I'm spending ON on my DFS or BFS. But I prefer to just spend ON if I can, right? So can we look at our dynamic programming that we had here and somehow extend this dynamic programming so that instead of just finding the diameter, it actually finds the farthest vertex to any given vertex? Now, this is the part where I told you dynamic programming is an art. You have to define your subproblems in a really nice way. So let me just copy my tree. Oh, I have so many things written on this tree, it's not copyable. Okay, let me copy this tree. Okay. I don't remember what these values were, but I don't need them anyway. So basically, what is the farthest vertex from 1? It's probably 7. From 2, it's also 7. From 3, it's 4, right? From 4, it's 7. From 5, the farthest vertex is 4. From 6, it's also 4. From 7, it's also 4. So what are we observing here? Remember, the diameter was from 4 to 7. But it seems that the farthest vertex from any vertex is one of the 2 endpoints of my diameter. Okay. So this is generally true, but I'm not going to prove it to you. You get to prove this on your own. So a non-dynamic programming way of solving this problem would be to first find the 2 vertices at the 2 endpoints of the diameter. So find U and V like this. And then you just find the distance from U to every vertex and the distance from V to every vertex. And because you know that the farthest vertex from any W is either U or V, you know which one to output, right? You just look at the maximum. But I want to use dynamic programming. Okay, this session is about dynamic programming. That's why I'm not giving you those proofs either. So how would you propose I define my dynamic programming subproblems? Well, here's what I can do. Let's take any vertex, for example, vertex 3. And I can say, well, I want to find the farthest vertex from this vertex, but this farthest vertex is either in the subtree of the current vertex or it's somewhere else in the graph. So let's just do a casework and let's define different subproblems for these two cases. Okay, so here's what I'm going to do. I say for every vertex V, I define two different dynamic programming subproblems. I basically define, let's say, I call them up and down. So let me first do down. So down of V would be the maximum distance from V to one of its descendants. So if I only have the vertex V and everything below it, if I only have the subtree of vertex V, how far can I get from V? Okay, so this is the maximum distance from V to another vertex in its subtree. So for example, if this is my vertex V, if 3 is my vertex V, the maximum distance would be 2 because it can go to 7. Now, this is what we called height before. Right, this is basically the height of the vertex V. So we know how to calculate this one. Now I'm going to define something else. I'm going to say up of V is the maximum distance from V to another vertex that is not in the subtree of V. And I call it up because this is like starting at V and going up first, right? So maximum distance from V to another vertex not in the subtree of V, outside the subtree of V. Okay. Now, we know how to calculate down values because they're basically heights. And we talked about this. We said that we can do a dynamic programming, we can do a bottom-up dynamic programming and calculate these things. So basically, if you remember, we have this recurrence relation. Down of V is 1 plus maximum of down of W, where W is a child of V. By the way, I write it like this. I mean, W is a child of V. Okay. So we already know how to calculate this one. The question is, how do you calculate these up distances? Okay, so what is up of V? Let me just take this one. Oops. I wanted to copy it, not cut it. Oops. Okay. I have this, and actually let me make my graph a little bit bigger. So let's say I have vertex 8 and a vertex 9 and like 10 and 11. And I want to calculate up of 3. Okay. So I want to start from 3. And I know that the first step I'm going to take is going up the tree to the parent. But then from the parent, where do I go? Again, I can do a casework. Maybe from the parent, I keep going up. Maybe there is something here, right? So maybe from 1, I keep going up. Or maybe from 1, I go to one of its other children, right? So if I want to find up of 3, I'm basically saying, what is the farthest vertex in this part of the graph from the vertex 3? I say that my first step is going to 1. But after I go to 1, I either keep going up, in which case I would get the farthest vertex in up of 1, right? So my total distance would be 1 plus up of 1. okay? Or I went from 3 to 1, but then in the next step, I'm going down, okay? But if I'm going down, I cannot go back down to 3. I have to go to one of the siblings of 3. I have to go to either 2 or 8, right? Because otherwise it wouldn't be a path. So if I go to 2, then I can do down of 2 from there. So I went to 2, and then I ask what is the farthest vertex that I can obtain by moving down from 2. And the same thing for 8. So in this case, what I actually get is 2 plus down of 2 and 2 plus down of 8. What's happening here? So from 3, I'm going to 1, and then I'm going to 2. So that's the 2 steps. And then from 2, I can go down as much as I want. So that's why I have 2 plus down of 2. Or from 3, I go to 1, and then from there, I go to 8, and then I can go as much as I want. So that's 2 plus down of 8. And of course, I want the maximum of all of these cases. That's what up of 3. Okay. Now, in general, if I want to calculate up of V for any vertex V, I can say it's the maximum of these cases. So either I go one step up to the parent of V, and then from there I keep going up. So 1 plus up of parent of V, or I go to one of the neighbors, siblings of V. So maximum of W is a sibling of V. 2 plus down of W. Okay. Now, this is interesting because we are now combining 2 different types of dynamic programming on trees. When I wanted to calculate the down values, we said that the down values are basically heights. So I had to start from the bottom of my tree and go up and calculate all the down values. So let's say I do that first. Now I have all the down values. Now, when I want to calculate the up values, the up value at B depends to some down values, but I don't care about those. I have already calculated them. But it also depends on the up value of the parent of B. So when I want to calculate the up values, I have to start from the top of my tree and go down. So this is now a combination of both directions of dynamic programming on trees. First, we calculate the down values by going bottom up, and then we calculate the up values by going top down. And of course, at the end of the day, when I want to output this thing, alpha of U, it's just the maximum of up of U and down of U, right? So I say from the vertex U, what is the farthest place that I can go? I either go up or I go down. So just take the maximum. And of course, the runtime is still ON, because calculating all the down values was ON. We've seen that before. And calculating this is also ON. But why? Why is this one ON? So let's say I have all of the down values already. I've spent ON for those. Why can I find these up values in ON? So this is the first time where we're talking about siblings. Right. Okay, so here's the thing. When I'm at vertex V, I definitely know the up value of the parent of V. So this part is O1, right? But I have to go over all the siblings of V, and then I have to take this maximum. So if I do it in a naive way, this can actually give me a runtime of ON squared. How can that happen? Like this. Suppose that I have a graph, and it's just one root with many children, right? And let's say V is one of these children. So if there are any siblings here, this maximum is going to take O(n) time every time. So for each one of these vertices here, I'm going over n-1 siblings, taking the maximum. That's terrible, right? But I could have done a better thing, right? Instead of calculating this maximum on all of the siblings, I could calculate it at the parent, right? So at this parent, I could say, what is the maximum of the down value among all the siblings, right? And I calculate it once, I can reuse it. But there is another problem here. And the problem is that when I say W is a sibling of V, it cannot be V itself, right? So instead of just keeping the maximum value, I have to keep the two highest values. I have to keep the maximum and the second maximum. So when I'm at this parent, I go over all of the children and I find the maximum down value and the second maximum down value, right? And then when I'm at each of the children, if this child is the child that had the maximum down value, then I know that among its siblings, I have to take the second maximum. Otherwise, I know that among its siblings, I have to take the maximum. So in every case, I have already calculated it. So that's how you can make this in O(n). So again, this part should be calculated at the parent. That's parent of V. And this gives me a total runtime of O(n). But again, your choice, you can just do two DFSs, find the two endpoints, and then do a DFS from those endpoints and find the distances. Okay, we're going to continue with dynamic programming. We're going to see more examples of dynamic programming. Here's another very classical example. It's called edit distance. So imagine that I have two different strings. So I have two strings S and T. S and T that are strings. And I somehow want to convert S to T. But each time I can either add a letter, or I can remove a letter, or I can change a letter. Okay, so we want to convert S to T. And the operations that we have are add. So I can add a letter anywhere in my string. Okay, so add a letter anywhere. Or I can remove a letter. Again, from anywhere. Or I can change a letter. So as an example, let's say that we have HKUST. I can change one letter. For example, I can change the U. I can get HKTST, for example. Then I can remove a letter. Maybe I remove the K. I get HTST. And then I can add some letter, again, anywhere that I like. Maybe I do HOTST. Okay. Now, I'm starting from some string, let's call that S. I want to get to some other string, let's call that T. And I want to do the minimum number of operations. So that's why it's called distance. It's like the minimum number of edits that I'm doing in order to reach T from S. That's the edit distance from S to T. So that's what you have to write in the output. The output is going to be the minimum number of operations to turn S into T. By the way, in some textbooks, they say you start from both S and T, you can do these operations on both of them. It doesn't really matter, right? So if you can change and add and remove in one string, or you can do it in both of the strings, it doesn't really make a difference, right? So adding to one string, like removing to another. So instead of saying that I want to convert S to T, I can say we want to convert S and T to the same string. Okay. Pretty much the same problem. Like it will be solved using the same technique. Now, okay, give me dynamic programming ideas for this. How would you do this? So let's just look at prefixes as before. Let's say that ans ij is the minimum number of operations if I only had the first I letters of S and the first J letters of T. So I want to turn the first I letters of S and the first J letters of T into the same string. Okay. It's the sub-problem, like the same problem with S from 1 to I and T from 1 to J. So I only have the first J letters here, and I have only the first I letters. Okay. So this is my S, and I'm looking at the first I letters. I don't care about anything that comes after that. And this is T, and I'm looking at the first J letters. Now let's look at the very last letter. Okay. Just like before, either this letter matches or it doesn't match, right? Now, I can say I want to change this last letter in only S or in only T or in both of them. And if I want to change, I can just change it, or I can insert something new, or I can delete it, right? So these are all the options that I have. Okay. Now, by the way, I just realized that it would be easier if I just go back to the previous version. We want to convert S to T. Again, same algorithm works for both of them. Now, this allows me to look at fewer cases because T is not fixed. So since T is fixed, I have this last letter of S, and well, I can say I want to match this last letter of S with the last letter of T or not, right? If I want to match the last letter of S with the last letter of T, then of course they should match. So the first case is that if Si is equal to Tj, then I can just take the answer for the first I minus 1 letters of S and the first J minus 1 letters of T. Okay. Answer for the first I minus 1 letters of S and the first J minus 1 letters of T. What if they don't match? If they don't match, I can either try to add something to the end of here, or I can try to remove this letter, or I can try to change it. Now, if I want to add something to the end of S, what would I add? Of course, I would just add the last letter of T, right? Because I want it to match. So if that happens, then this last letter of T matches with the new letter that I have added here. And then I have to match the last J minus 1 letters of T. with the I letters of S. Okay. So if Si is not equal to Tj, what do I have? I can basically look at the answer for the I minus 1 letters, I letters of S and J minus 1 letters of T, but I need a +1 because I did an insertion in S, that's one operation. Okay. I could also delete this last letter from S. And if I do that, then I have the last I minus 1 letters of S, and I have, I have the first I minus 1 letters of S, and I have the first J letters of T. So I would just get the answer for I minus 1 and J, again, +1, because I'm spending one operation to do the division. Or I can just match them, right? And if I match them, that's basically saying that I want to change this letter to match the last letter of T. That's also one operation, but then I have to match the first I minus 1 letters of S with the first J minus 1 letters of T. So I would get the answer of I minus 1, J minus 1 plus 1. Okay. Now, of course, my final answer is going to be the minimum of all of these because I want to do as few operations as possible. So I'll take the minimum of these and I say this is going to be the answer for IJ. Okay. But here's the thing, we have to be careful. When the last letters are equal, when SI is equal to TJ, if I just say I will always match them, is that always optimal? Now, the answer is actually yes, you can prove it greedily, but suppose that I don't have a proof for it, right? If I want to just do dynamic programming, if I don't want to put any greedy into my dynamic programming, I have to also consider the case that these two are equal, but I'm still inserting or deleting or changing. Right? Well, I wouldn't change, but either inserting or deleting. So even in this case, I would add the case where I'm inserting a letter here. So that would give me ans of ij minus 1 plus 1. Or the case where I'm deleting this letter, which gives me ans of I minus 1 j plus 1. And again, I take the maximum of all of these. And I say that's ans of ij. Okay. Now, again, sorry, the minimum. No, maximum would be off. Yeah. Again, you can go and try to prove that the minimum is always this one, but it doesn't matter because my runtime is going to be the same anyway. When I'm calculating ans of ij, I'm spending constant time, right? And how many subproblems do I have? Well, n squared, or like the length of S times the length of T. So that's my runtime. Okay. Now, instead of saying that I want to convert S to T again, I could have said that I want to convert S and T to the same string. Then you could do more cases. You could say, what is the change that I'm making to S? What is the change that I'm making to T? Right? But you will have a very similar DP and it will actually give you the same answer. So it's the same. Okay. Now I'm going to give you even more examples. So let me give you some examples of tiling. So let's say that I have a rectangle and this rectangle is 1 by n. And I want to fill up this rectangle with a bunch of dominoes. Okay. And a domino is basically a 2 by 1 rectangle. But I can also put some gaps in there. Okay. So for example, I can put a domino like this, and then I can put a gap of 1, then I can put another domino. But then next time, maybe I don't put a gap, I just put another domino. So every domino has a width of 2. And I want this to be full in the sense that you can only have gaps of length 1. Okay, so no new domino should fit into this. Now, the question is, how many ways do I have to do this? So my input is just the number n, and the output is the number of possible tilings of this 1 by n grid with dominoes. And again, in these tilings, I can have empty spaces, but I shouldn't be able to fit a domino into those empty spaces. Okay. Yeah, well, this is not too hard, right? So it's kind of obvious what my subproblem is going to be. I'm just going to say, suppose instead of 1 by n, it's 1 by I, right? So ans I is just the subproblem on a 1 by I grid. Okay. Oh, and by the way, I forgot my base cases here. Don't forget them in the exam. I always write your base cases. Okay. So if I have a grid with I squares, what can I do with this grid of I squares? Basically, I have to decide where to put my last domino, right? So I have this grid, and let's say that I have indexed all of these grid cells 1, 2 to I. And now I can put my last domino at the very end so that it covers I and I minus 1. Right? Or I can say I want to put some empty space. And if I want to put some empty space, I'm going to put I as empty, and then I'm going to cover I minus 1 and I minus 2. Right? So based on this, I can say that ans I is equal to, well, the first case was that I covered this one and this one. So I have I minus 2 remaining places. I can decide how to cover them up. So this is just ans of I minus 2 plus. The second case was that I let this one be empty and I cover these two. So I have I minus 3 remaining places. So this is ans of I minus 3. And again, you can do the base cases on your own. Just do 1, 2, and 3. Make sure you do at least 3 base cases because you need this to work. Okay, so this was simple, and we can calculate it in ON. Let me see. We have 5 more minutes. I want to also do set cover. So this is also a very classical problem. It's actually an NP-hard problem, and we will learn about NP-hardness soon as well. So my input is basically this. I have a bunch of subsets of the numbers from 1 to n. Okay, so let's say I have k subsets. K subsets S1, S2 to Sk, and all of them are subsets of the numbers from 1 to n. Okay. Now I want to pick some of my subsets so that they cover all of my numbers. But I want to pick as few of my subsets as possible. Okay. So the output is going to be the minimum, I don't know what to call it. Let's say R, such that there are R subsets. Let's call them SI1, SI2, to SIR such that the union of these subsets is the whole set from 1 to n, such that the union of Sij is basically all of my numbers, j from 1 to r. And of course, again, I want to minimize r. So I want to take as few subsets as possible so that they cover everything. And the question is, how many do I need? Well, here's one simple solution. Let's brute force it. Let's try every possible subset of these subsets, right? So I have 2 to the power of k choices for which subsets to take. And for each of these choices, I can just calculate the union and just see if it covers everything. And let's say I start from small to big so that as soon as I found the answer, I can output it, right? So this is my first solution. Just brute force it. And this is actually going to give you a runtime of O(n) times 2 to the power of k, because you're looking at 2 to the power of k different solutions, and just takes O(n) to calculate the union and see if they cover everything. Actually, n times k? Yeah, it takes n times k to the union, because maybe they're all really big and maybe they all cover everything. Yeah. So anyway, the 2 to the power of k is big here. So this wouldn't work if you, well, this would only work if you have very few subsets, right? But what if I have the opposite situation? What if I have very few numbers, but I have a ton of subsets? Okay, so imagine that k is big and n is small. Can I find a better solution in that case? Well, yes. And I'm going to do something similar to this previous case where I'm looking at subsets. So here's what I'm going to say. I say for every I between 1 and k, and every subset S of the numbers 1, 2 to n, define this. Let's say that dp of is is going to be equal to the minimum number of subsets that I have to take if I can only choose from the first I subset. So I can only choose S1, S2 to Si. And if I have to cover S, I don't have to cover everything. I just have to cover this one. Okay. I'm not going to write it because we don't have time. But how do you calculate this? Well, you have dp of is, which means that you have this set S that you want to cover, and you have a bunch of subsets. You have S1, you have S2, let's say S3, so on to Si. Okay, so this is very similar to knapsack. You say either I take this last subset Si or I don't. If I take Si, it's going to cover part of S. So with the other I-1 sets, I have to cover the rest of this. Okay, so this is going to be 1 because I'm taking Si plus dp of I-1 S minus Si. Or I'm not taking the last subset. I'm not taking Si into my solution, which means that I have to cover all of S with the first I-1 subsets. So that would just be dp of I-1 S. And again, of course, I want to do minimum because I want to choose as few subsets as possible. Now, what is the runtime here? I mean, you can see that this is just the minimum of 2 things. So I'm spending O1. The question is, how many subproblems do I have? I have k times 2 to the power of n subproblems. Because I can go from 1 to k, and S is a subset of 1 to n. So it's 2 to the power of n possibilities for S, and k possibilities for I. So the total runtime is O of k possibilities for I times 2 to the power of n possibilities for S. Oh, actually, this is not just O1, even though it's the minimum of two things. Unfortunately, I have to find this set. I have to find S minus Si, right? So I have to take my set S and I have to remove everything in Si from it. So that's like a factor of n. So k times 2 to the power of n times n. That's my total runtime. So my dp of is only depends on two previous dp values, but just to figure out which two, I'm spending O(n). That's why the total runtime is like that. Okay, I'll see you tomorrow.